In the vast expanse of the cosmos, from the smallest particles to the largest celestial bodies, a fundamental concept governs the behavior of matter density. Density, simply put, tells us how much stuff is packed into a given amount of space. It's a measure of how tightly matter is squeezed together. Understanding density unlocks a deeper appreciation for the world around us. It explains why a massive ship can float while a tiny pebble sinks. It helps us comprehend why certain materials are used in specific applications. Density is a key that unlocks a treasure trove of scientific knowledge. From the air we breathe to the ground we walk on, density plays a crucial role in shaping our physical reality. It's a concept that transcends disciplines, influencing fields as diverse as physics, chemistry, engineering, and even astronomy. In this exploration of density, we'll delve into its definition, explore the concepts of mass and volume, and uncover the intricate relationship between them. We'll journey through real-world examples, witnessing density in action, and ultimately, grasp the profound significance of this fundamental concept. Density, at its core, is a measure of how tightly matter is packed together. It quantifies the amount of stuff or mass contained within a specific amount of space or volume. Imagine two objects of the same size, a fluffy cotton ball and a solid metal cube. Intuitively, we understand that the metal cube feels heavier than the cotton ball. This is because the metal cube has a higher density. Its atoms are packed more tightly together, resulting in a greater mass concentrated within the same volume. Density is expressed as a ratio of mass to volume. A denser object will have more mass packed into the same volume, while a less dense object will have less mass spread out over the same volume. This concept of compactness is central to understanding density. It's not just about how much stuff an object has, but how tightly that stuff is squeezed together. In the next sections, we'll delve deeper into the concepts of mass and volume, laying the groundwork for a comprehensive understanding of density. Before we can fully grasp density, we need to understand its building blocks: mass and volume. Let's begin with mass. Mass is a fundamental property of matter. It's a measure of how much stuff an object is made of. Imagine a bowling ball and a tennis ball. The bowling ball has more mass than the tennis ball. It's made up of more atoms, more particles, more stuff. Mass is often confused with weight, but they are distinct concepts. Weight is the force exerted on an object due to gravity. Mass, on the other hand, is an intrinsic property of an object, independent of gravity. Think of an astronaut in space. They are weightless, but their mass remains the same. They are still made up of the same amount of stuff. Mass is typically measured in kilograms or grams. It's a fundamental quantity in physics and plays a crucial role in understanding the behavior of matter. In the next section, we'll explore volume, the other key ingredient in our recipe for understanding density. Now that we've explored mass, let's turn our attention to volume. Volume is a measure of how much space an object occupies. Imagine a balloon filled with air and a marble. The balloon, even though it may be lightweight, occupies a larger volume than the marble. It takes up more space. Volume is a three-dimensional quantity, often measured in cubic meters or liters. It quantifies the amount of space an object occupies in all three dimensions: length, width, and height. Think of a box. Its volume is determined by multiplying its length, width, and height. The larger each of these dimensions, the larger the volume of the box. Volume is an essential concept in understanding density because it provides the space in which mass is distributed. With a firm grasp of both mass and volume, we can now delve into the relationship between them and uncover the secrets of density. Section 5. Mass versus volume, distinguishing between the two. Mass and volume, while distinct concepts, are inextricably linked. Mass tells us how much stuff an object has, while volume tells us how much space that stuff occupies. Think of a sponge. A dry sponge has a certain mass and volume. Now imagine soaking that sponge in water. Its mass increases because it's absorbed water, but its volume remains relatively constant. This example highlights the key difference between mass and volume. Mass is about the amount of matter, while volume is about the space occupied. Understanding this distinction is crucial for grasping density. Density isn't just about how much stuff an object has, but how tightly that stuff is packed into a given space. In the next section, we'll see how mass and volume work together to determine an object's density. Section 6. Calculating density, mass and volume in harmony. We've explored the concepts of mass and volume, the building blocks of density. Now let's see how they combine to define this crucial property. Density is calculated using a simple formula: density equals mass divided by volume. This formula tells us that density is the ratio of an object's mass to its volume. A denser object will have a higher mass for a given volume, while a less dense object will have a lower mass for the same volume. Let's consider an example. Imagine a gold bar and a block of wood, both with the same volume. The gold bar, being much denser than the wood, will have a significantly higher mass. This is because the gold atoms are packed much more tightly together than the wood fibers. Density is typically measured in kilograms per cubic meter or grams per cubic centimeter. It's a quantitative measure of how much stuff is concentrated within a given amount of space. In the next section, we'll explore real-world examples of density and see how this concept plays out in our everyday lives. Section 7. Density in action, real-world examples. Density is not just a theoretical concept confined to textbooks. It's a fundamental principle that governs the behavior of matter in our everyday lives. From the air we breathe to the objects around us, density is constantly at play. Consider a helium balloon. Helium is less dense than air, which is why the balloon floats. The buoyant force of the air, which is denser, pushes the balloon upwards. Think about oil and water. Oil is less dense than water, which is why it floats on top. This density difference is also why oil spills can be so difficult to clean up. These are just a few examples of how density manifests itself in the real world. From the floating of ships to the sinking of rocks, density plays a crucial role in shaping our physical reality. In the next section, we'll delve deeper into the concept of buoyancy and explore how density determines whether an object will float or sink. Section 8. Floating and sinking, buoyancy and density. Density is tied to buoyancy, the upward force on an object in a fluid. Buoyancy lets ships float and balloons soar. Floating or sinking depends on density differences. Less dense objects float, denser objects sink. A rubber duck floats because it's less dense than water. The water's buoyant force pushes it up. A denser rock sinks. Density determines floating or sinking. Section 9. Density in everyday life. From cooking to construction. Density's influence extends far beyond the realm of science classrooms and into the heart of our everyday lives. From the kitchen to construction sites, density plays a subtle yet significant role. Consider cooking oil. As we've discussed, oil is less dense than water. This density difference is why oil floats on top of water, making it ideal for frying foods. The hot oil cooks the food, while the denser water below prevents it from burning. In construction, density is a crucial factor in choosing materials. Concrete, for example, is a dense material that's strong and durable, making it ideal for foundations and other structural elements. Even in medicine, density plays a role. Bone density scans, for example, are used to diagnose osteoporosis, a condition that weakens bones and makes them more prone to fractures. These are just a few examples of how density permeates our daily lives. From the food we eat to the buildings we inhabit, density is an invisible force shaping our world. In the next section, we'll explore the broader importance of understanding density and its applications across various disciplines. Section 10. The importance of density, applications across disciplines. Understanding density is not merely an academic exercise. It's a fundamental concept with profound implications across disciplines. In physics, density is crucial for understanding fluids, buoyancy, and pressure. In astrophysics, it helps study stars and planets. Chemists use density to identify substances. Engineers use it in countless applications. From designing ships to building skyscrapers, density ensures structural integrity. In environmental science, it's crucial for studying weather and climate. Density helps unravel the mysteries of our universe. Section 11. Conclusion: density, a key to understanding our world. From the smallest atoms to the largest galaxies, density is a fundamental concept that governs the behavior of matter. It's a key that unlocks a deeper understanding of the physical world around us. We've explored the definition of density, delved into the concepts of mass and volume, and witnessed how these factors intertwine to determine an object's density. We've journeyed through real-world examples, from floating balloons to sinking rocks, witnessing the profound influence of density in action. Density is not merely a scientific abstraction, it's a concept that permeates our everyday lives, influencing the materials we use, the food we eat, and even the very air we breathe. Understanding density empowers us to make sense of the world around us. It allows us to explain why objects float or sink, why certain materials are used in specific applications, and how the universe itself is structured. As we continue to explore the cosmos and unravel its mysteries, density will remain an indispensable tool in our quest for knowledge. It's a testament to the elegance and simplicity of the laws that govern our universe.